Alright everyone, so in this video I'm going to do an overview of the computer algebra package Sage, and when I'm finished with it I'll go and have a sample, the worksheet that I'm gonna do here. I'll put it into WildCourses and then I'll give you this list of commands, kind of an overview of some basic commands, and then at the bottom of the page there are 15 problems for you to work on. So at the end of this, um, make a worksheet that works out all 15 of these problems effectively. Okay, so the first thing that I'm going to do is open Sage up. Okay, so typically this is the command that you'd want to use if you were using a Mac. If you're using Windows, the command would probably look something similar. If you're using not version 9.0, you'll just want to change the number here to be whatever version you're using. Okay, so now what I'm going to do is I'm going to go and open a new worksheet. Okay, so now we're just going to go and work through a bunch of the commands that we have here. Right, so the first one, it just gives us all of the arithmetic commands. Right, so for example, we would have 2 cubed is 8, 2 times 7, 42 divided by 6, so we would get 8, 14, and 7, all as we would expect. Square roots, we just put a squirt out in front, so square root of 9 is 3. Let's see, sines, cosines, and tangents. If I remember these correctly, they all work in radians. So if I take sine of pi over 2, I should get 1. But if I take sine of 180, it'll give me something that's not 1. Because these ones all work in radians by default. Let's see, so natural logarithms. So let's say I have the natural logarithm of e to the 3. That should give me back 3, which is exactly what I want. Good. Okay, so let's go and make some functions. So I first have to declare that x is a variable, and then I can make the function f of x equals 3 times x plus 7. And let's see, so we want to say get f of 10, so we would expect this to be 3 times 10 plus 7, so I'd better get 37, which is exactly what I get. Let's see, so then we can solve some equations. So for this one, we're going to go and solve a system of equations for two variables, x and y. So I want to solve the system of equations 3 times x plus 7 times y equal 12. And I realize that in the file that I have written here, I'm missing the stars for multiplication. 8 times x minus 5 times y equal minus 3. And I want to solve this for x and y. And I need to define y as a variable. So now y is nicely defined as a variable. There we go. Right, so what this says is that the solution to the simultaneous solution to 3x plus 7y equals 12 and 8x minus 5y equals minus 3 is x equals 39 by 71 and y equals 105 by 71. So we can just verify that quickly. All right, so x equals 39 by, let's go and do this. Let's just print 3 times 39 divided by 71 plus 7 times 105 divided by 71. And we'll also print 8 times 39 by 71 minus 5 times 105 by 71. Right, we get 12 for the first one, and we get minus 3 for the second one. So we found the solutions for x and y for this system of equations. If we wanted, if we instead had just one function, and we wanted to solve it for just one variable, we could solve it for x, which would give us x in terms of y. Okay, so then what else do we want to do? We could find some roots. So let's take f of x to be the function, let's take x squared plus 5 times x plus 6. So if we wanted to factor this one, we would factor it just using our standard binomial methods. So let's print f dot roots. Yes, and also if you're unsure about a command, you can press the tab key. So you just write an f dot and then press the tab key, and it'll pop up that little menu of, of possible commands. Right, so here what this says is f dot roots is telling us that minus 3 is a root of multiplicity 1, and minus 2 is also a root of multiplicity 1 for f. Right, so we could write f dot factor, f of x dot factor, there we go, and we would get x plus 3, x plus 2. So that would be another way to see that the roots of f are minus 3 of multiplicity 1 and minus 2 of multiplicity 1 as well. Suppose that we took g of x equals x plus 3 times x plus 2 squared. We could expand g. So we would type g of x dot expand, and it would give us this expanded polynomial. Okay, and then we can also plot a function. So let's take the g of x that we've defined and let's plot it. So let's plot g of x. I'll plot x from, let's go with minus 4 to minus 1, because we said that the roots for this are going to be minus 3 and minus 2. So we'll plot it around there. And let's make the color dark green. Right, so we get a plot that looks like this, and what we see is that the function is 0 at minus 3, and it's also 0 at minus 2. Let's see, what else could we do with this? Well, let's go and add a tangent line onto this, because I do ask you to plot, let's see, yeah, I ask you to plot a tangent line on the same plot. So let's go and include how you would do that. So what's nice about this is you can add plots together. So let's say that I have P1 is my plot, of g of x. So I'm just going to change the domain for the moment, and I'm going to define a second plot, and this is going to give me the plot of the tangent line. Let's see, so we need to get a derivative, and what I'm going to do, let's see, so I'm going to take g of x dot diff, and I'm going to evaluate it at minus 1.5. So I'm going to get the tangent line to this function at 1.5. Let's see, times the value x minus 1.5 plus g of 1.5. You can use 1.5 or 3/2, it won't matter. And I'm going to plot this from x going from -3 to -1. I'm going to color the tangent line dark red, and I'm going to make the line be a dashed line. So I write line style equals double dash. And then what I can do is I can add these two plots together just with the plus operator and show them. Right, so what we see here is that my red line is the tangent function to the green curve, and exactly at 1.5, the green curve and the red line have the same slope, and they evaluate to the same number. Okay, and then the last thing that we just want to do here kind of quickly is let's go and find a limit. Okay, so let's say that I take f of x to be, well, we've used the function x times x minus 3 a few times. Let's see, no, I'll pick something better. Let's see. Let's take x squared plus 5x plus 6. So we'll take a rational function, and we'll divide it by, what do I want to divide it by? I'm not sure what would it expand out to. Let's take x minus 1 times x plus 3. So that way um, the function will be undefined at x equals -3. It'll be 0 in the numerator, 0 in the denominator, but from what we know about limits, the limit would factor nicely. Right, so let's first just print f of x. Okay, and if we wanted, we could print fx dot expand, so that should expand out my denominator. It expanded it out too much. That is one thing to, I guess, be wary of, is sometimes when you expand, computers are kind of dumb and they do bizarre things like this. Or we could factor it and say, we'll cancel the x plus 3 factor in the numerator and denominator, get x plus 2 over x minus 1. So I'm going to find the limit of this as x goes towards -3. And from what we know about limits, this will give us -3 plus 2, all divided by -3 minus 1. So we should get -1/4 for our limit here. So I'm going to find the limit of f of x equals -3, and I get 1/4. So I get, so I get my -3 plus 2, all divided by -3 minus 1, so 1/4. Okay, and then the last thing that I want to do is just show you how you could use this to find derivatives. So let's see. So up here we had our g of x. I'm not going to use this one. I'll define f of x to be minus x times x minus 3, which is something that we found the derivative of for before. So if I want to find the derivative, I could do it by writing f of x dot diff, which is saying to differentiate. So our derivative function is, as is typical, minus 2x plus 3. So we found that using our limit definition. So let's go and also just verify this. So let's take, first I need to declare the variable h. And I'm going to take the limit of f of x plus h minus f of x all divided by h. One of the other nice things that you might see about Sage is that whenever I open a parenthesis, I need to close it. And what's nice about this, is, as you might be able to see, is that when I've got the cursor by a parenthesis, by a closed parenthesis, the corresponding opening parenthesis is highlighted in green. So it just makes it kind of nice if you, just nice to make sure that you don't have any parentheses that are open. Okay, so we have our quotient f of x plus h minus f of x all divided by h, and we're taking the limit as h goes to 0. And we'll print it. Right, so what this says is that our limit definition gives us the minus 2x plus 3, which is exactly what the derivative is. So what we can do is we can use all of these various techniques to go and simplify out some of our work. And what's nice about this is learning how to use some computer algebra packages. It's useful for checking your work for our class, but you can also use it if you're going on to other classes, so Calc 2, or maybe you're doing differential equations, linear algebra, something like that. Okay, so I think you have everything you need here to solve these problems. If you have any questions about how to do anything with Sage, send me an email and I'll answer it as quick as I can. Tomorrow, at some point, I will be hosting a review session for our test on Friday. If you have any questions, the test is going to go up to everything that we've covered so far. I'll let's see, I will try and post a study guide. Yeah, I should be able to post a study guide into WILE courses. I might have some past tests that I could put there, but I think if you just going back through the worksheets that we've done so far is probably a good way to go about studying for the test. And again, if you have any questions about anything, just drop into the Zoom call tomorrow, and I will put an announcement in WILE courses when I'm going to host it. Okay, and I will see you all possibly tomorrow.